All right, so Tom got to provide the nice theoretical overview, or the broad overview. I'm going to be about as much math as you guys have had since grad school or undergrad. So it's before I do that, though, I wanted to mention, when I talked to Ashley, we've done training on how to use the software here before. Some of the younger people here have never had that, maybe. So the training we're doing, we're going to have some hands-on stuff like Tom was doing, but a lot of it is not going to be. So I wanted to point out, you guys may know this already, but if you come to our website, powerworld.com, you just come to the regular website. If you go over to training and events and then online training, along the left, you'll see some various courses that we have, one of which is a transient stability course. Actually, most of the video that's on here was recorded here in 2015. You guys did this. Basically, when BPA says, can I take the training, I always say yes, as long as you give it to us so we can share it with our other customers too. So if you come in here and you wanted to learn more about, transient stability basics, you'd come in, click here, and there will be, there we go. You click on here, there's a YouTube video on all of our training for all of our courses. Above the YouTube video, there'll be 2 links, one of which is slides that were used in recording this video, and then updated slides, because, over time we update them, but we don't re-record because that's a bigger process. So if you click on here, I suspect this is BPA 2015. Yeah, there it is. You guys did went all out producing it and everything.
How's Gordon doing?
So this is Tom. But anyway, you can go in here.
All that music is
Yes, they added the music after. Tom didn't come out to a light show. But anyway, that's all on our website. You can go do that. You can, bother your neighbors who are more experienced. But all of the click here, do this, that really just software training is all on our website. All right, so I wanted to make sure you knew that. All right. So this presentation is the presentation I wish I had in grad school, because it's presented the way I understand it.
We're going to go all the way back to how to how synchronous machines work. And we're going to start with synchronous machines because that is the vast majority of the devices that turn mechanical energy into electrical energy. As a new engineer, the fact is most of the new generators you deal with are solar and wind right now. But most of the generators that are in the existing fleet are some sort of a synchronous machine. And there's a huge amount of literature on this dating back 100 years, really even 120 years. So a couple good books. The 2 books I tend to go to first the book I go to first on any topic in transient and dynamic stability is Kundar's book, just because it's the biggest one. It covers DC lines, loads, it just covers a very wide set of things. It's a good reference book. I suspect most of you have it. It's actually not a good classroom book because the reason people buy textbooks like Tom is for the homework solution guide and the things at the end of the textbook, because that's less work for him. Whereas this book is not, it's not really, it's a reference book. It has homework problems, but it's a great reference book. A good theoretical book on synchronous machines is my old professor, Professor Pye, and Sauer wrote a book, and a lot of the reason I like this one is because the nomenclature tends to follow what actual commercial software does. I'm not positive they chose that on purpose, but it matches better what is actually written in code like PowerWorld, PSLF, and PSSC. So a lot of the derivation I walk through really comes out of this book. All right, a few topics. There's a lot of words in synchronous machine worlds. There's talk about stator and rotor. Stator and rotor really have to do with, where is the thing physically located. In the vast majority of synchronous machines, there are other terms related to the armature and the winding. These are functional terms. Most of the time, I'll present in a couple slides, the armature is the stationary part of the generator, and the rotor will have the field winding on it. I assume it's possible to flip that. And actually,
DC motors.
DC motors will flip it?
Is the rotation.
Okay. Yeah, but so functionally, as a power engineer dealing with these big synchronous machines, you tend to think armature is the stator. It doesn't have to be true. It is true in the motors we deal with, or generators we deal with. All right, there are then other windings we're going to talk about in the math coming up. They're called damper windings, is what I like to call them. Mostly because when you say amortiseur, nobody knows what you're talking about. I assume that's just the French word for damping. Does anybody know? So anyway, it's an extra winding that's added that we'll talk about in a little bit, that basically makes the machine want to be at 60 hertz. So if you move away from 60 hertz, it creates a torque that tries to bring you back. It's good for stability. It's also good for startup. If you think you start out at 0, this winding is creating a torque that's bringing you up. So it wants you to go to 60 hertz. So it was created, engineers figured out, hey, if I add a winding here, it makes my machine behave better. Yep.
Jamie, I'm pretty familiar with the damper windings on our hydro machines because of the way the rotors are set up. But on the big steam units where they've got those buried round rotor type things, do they still have a damper winding in those?
I think so.
I've never seen one. I used to work for GE.
They're not in there? Okay.
I never saw an amortiseur winding in a steam turbine or gas
Okay.
rotor.
Okay. I mean,
They might have a few that exist, but I would say typically not.
Yeah, I mean, I'll kind of have pictures of where they would be if they're in there. Some of the models we have, we don't include those. The model that we're going to derive here is it's going to have the field winding, and it's going to have 2 damper windings on the Q axis and 1 on the D axis. Depending on how you set up the parameters, you're essentially saying some of those damper windings are not there, depending on the input parameters. And then another topic is poles. If you want your machine to spin more slowly, then you're going to have extra poles. Actually, let me just show some pictures up here in a second. So like here is a round rotor where it's saying there's RST. My hunch is I copied this off in a different language. I bet they use this instead of ABC. Right?
It's European.
It's European? Okay. So the A phase is right here. The B phase coming out and going in is right here. And the C phase is right here. So there are 3 phases, and there's one, actually they call this a 2-pole machine, because each winding has 2 poles. In a winding that would spin more slowly, like a hydro plant would normally be like this, you'll have many poles. And what is the maximum number of poles that someone might have?
I forgot what it was, but it was a lot.
It was a lot. So they might have literally 4 or 5, or 4, 6, 8 poles. Even more? Okay. Yeah. So if you have more poles, it basically means that you can spin more slowly and still create a 60 hertz waveform. So poles show up. Now, once you get to the models we have, all of that is going to go away, but there's a whole bunch of math that goes into there. So, all right, to start with, let's just assume we have a 2-pole machine. So we have A phase, the dot and the arrow, these represent windings. So if you remember, make sure you use your right hand, put your left hand behind your back. The arrow's coming out here, so we have current that's going like this, kind of down the armature, up and back out. And we create the A axis then is the right hand rule from that. The B axis is right here. It's going like this, so the B axis is up this way, and you can draw these positional axes that way. And then finally in the middle we have a rotor. The rotor winding is coming, the arrows are going in and out this way, so the D axis is in this direction. All right, from there, so the D-axis is related to the rotor, and these A, B, C are related to the stator, or the armature on the outside. All right, we then need to choose some other things. The Q-axis. All right, the Q-axis is chosen as being 90 degrees out of phase with the D-axis. So then we have to make a choice. Do we make it behind, or do we make it in front? Leading, lagging is what people like to use the term. So we're going to use leading, and we're going to put the Q-axis in front of that. That is an arbitrary choice. After that, we need to define what is the rotor angle of the machine. And again, it's like, well, how do you define it? It's like Tom's slack angle. Angles have to be with respect to what? And the rotor angle is defined in the equations we use as the angle between the A-axis and the Q-axis. So it's this angle right here. All right, be careful. When I first started, so kind of the history of transient stability, Power World existed from '96 until probably about 2006, and we didn't do anything with transient stability. A couple things happened at that point, kind of three, two of which really are just kind of random. First of all, we could see wind and solar was starting to pick up, and that was meaning more people were doing transient stability. So, I mean, if I came to BPA in 1996 and I had a room like this, probably 2 or 3 of you would ever run transient stability. Is that fair, Dimitri? Huh? More? Okay. But it was, my point is it's grown. Probably twice as many people are, or more. Many utilities just didn't do it at all. So from our commercial standpoint, it was like, okay, there's going to be more customers. That was the good reason to do it. The other reasons we started doing it is Tom got called and he's like offered to be on the textbook, but he had to write the book on transient stability, the chapter on that. So then Tom was like, oh crap, I need to remember how transient stability worked, because that was not the field that he worked in at that point in his career. So he had to go back and remember how it worked. And so naturally that got into simulator. And the other issue is we were trying to sell to China at the time, and our folks in China told us you can't sell the software tool without transient stability. The irony is we did sell it there and no one ever bought transient stability. So that wasn't a good reason. All right, so at that point, then Tom's looking it up. You know, a couple years later, I started looking at it as well. If you look at textbooks on this topic, those two choices I just made about where is the Q-axis, is it leading or lagging, and where is the rotor angle, the textbooks define it differently. In Kundar, he defines the Q-axis leading, but when he talks about rotor angle, he talks about this angle instead of this angle. It's not wrong, it's just an arbitrary choice. So what he calls rotor angle is really 90 minus our rotor angle. If you go look at another book, the Anderson-Fuad book, they define Q-axis as lagging. Again, perfectly fine. The reason I bring it up is if you take equations out of Sauer's book, or the equations I'm going to present, and then go look at the Kundar or Anderson-Fuad book, we're going to have random sign differences all over the equations. And some places they say Q, we'll say D. And it's wildly confusing as a new person coming into this very technical field that the textbook nomenclature really isn't consistent. So be careful if you look at that. All right, basics of the synchronous machine. So the synchronous machine kind of has two main inputs to it. I should say that the output is on the armature. That's the power going out into the system. The two inputs are we have some device that is creating a DC voltage to apply to the windings on the rotor. So this goes all the way back to like high school physics class where you took a piece of iron, wrapped wires around it, and hooked up your battery when you were like 16 years old. And then you sat and spun that device and you created some power coming out of it. So this device, we call it an exciter, is creating this DC voltage here. We then have another device somewhere that's applying a torque to spin this rotor. And we call that device a turbine, and there's a control system on it called the governor. So we have some mechanical power coming in here, spinning a rotor that's got a DC voltage applied, and that's going to, because we've got a DC voltage that's spinning, that's going to create an AC voltage going out on the ABC phases of this device. And that's the basics of a synchronous machine. So Tom later is going to talk a lot about the exciter and the governor. I'm, in this presentation, only going to be talking about, well, how do we model the physics of this rotor as it's spinning? All right. Comment about the rotors. Rotors are created in different ways. Some rotors are round rotors. They tend to be bigger machines. Again, I'm kind of just talking about why are they round? My hunch is because they're really big, and mechanically it's easier to make them round. Is that why?
Really, really fast.
Yeah. So if you were spinning this really, really fast, unless you produced it perfectly symmetrically, you would get vibrations. Whereas if you don't make this perfectly symmetrical, you'll get less vibration.
And it's also, I think they can't. The one on the bottom, the way they connect those pole pieces, there's a sliding keyway and whatnot. If you're spinning really fast, they don't.
They'll break. The mechanical engineers figure this stuff out.
Yeah, it's impressive.
Yes. So basically, really fast spinning devices will be round. The hydro units, which spin a little slower, will tend to be this. This has an advantage because there's less iron and it's cheaper as a result, whereas this is more expensive to make. So one or the other you will have. It has an impact on the equations we'll talk about. The equations we derive really are for both of these. And then if two values happen to be equal to each other, then you're modeling this versus this. And we'll kind of walk through that. So this is, just went out. I think Tom got these. This is a big synchronous machine. So the stator's going this way. You can kind of see the windings in here on the stator. This is the big, giant stator. That's huge, yeah. That's a big old, probably for a nuclear power plant, is my guess. Synchronous machine rotors, you can design them like this. There's the slip rings you're kind of talking about on a
Keyway, spider.
The pole pieces, you call them? Okay.
So the top part would be a pole piece, and it would slide into the spider. We call the thing that has the little things that slide, pole piece slide.
Okay.
So
Yeah.
the center.
So this is for a salient rotor, and this would be more where you've got the windings in here. Actually, I think this is meant to represent like a permanent magnet rotor, where these pieces are actual magnets. But anyway, there's different ways to actually build the rotor itself. This is a picture of a rotor. This would be more salient. Actually, I'm learning things. So these are the pole pieces that are getting put on there.
Yeah.
And clearly there are a lot. If I were to count all these and divide by 3, that's the, divide by 6, I guess, actually. That's the number of poles. So there's a lot of pieces on there. This is probably a 12-pole rotor.
Actually, each pole would be a pole, because it's the DC, right? It's the DC.
Well, correct, but there's one on here and one over here, and that's,
Pole pair.
oh, you're right, pole pairs, yes. So, yes, so you just count them all. Wow, so that's probably like a 60-pole machine, something like
It
that.
looks like it has an exciter one.
This, I think, is meant to be the
That looks like
exciter.
a DC one
Yeah.
of some sort. So it might have an integrated, it's old, might have an integrated exciter.
Yeah, so guessing this is creating the DC voltage which is being applied to this rotor.
And then you can see the amortisor winding on the very end there. It doesn't show up very prominently.
Like the ones winding this way, you mean?
Yeah, there's just bars in the pole, face of the pole piece. And you can kind of see some horizontal lines in the whole piece,
Yes.
and that's where they're driving the mortise or winding.
Okay.
And it's like a squirrel cage winding, so on the very end of the pole,
Yep.
you can see sort of where the squirrel cage,
You're
the
just
mortise
winding.
or winding has been bolted together
Yeah.
all around.
Okay. Okay, so this is what it physically looks like. And then what we're going to derive in the equations, we're not really going to talk about how's it physically made. They figured that stuff out 80 years ago, and there's probably 6 or 10 companies in the whole world that know how to build one of these things. So mathematically, we're going to think of it as we have the ABC phases. We've got the field winding. This is the one that the external exciter is actually hooking up to provide a DC voltage in here. And then our equations, we're going to say, well, they might have another damper winding in the D-axis, and they might have up to two damper windings in the Q-axis where they're wound like this instead. So the D-axis are wound in the same way as the field winding, and the Q-axis windings are 90 degrees out of phase. I shouldn't say out of phase, just physically they're 90 degrees different from that. So we have two Qs and two Ds, and one of the D windings is actually physically connected to the exciter. And that's basically the equations that we have. So we start there, and then we just start applying math to it. The first equation for math is the easiest one, because it's just Newton's method. It's force is mass times acceleration, except we're dealing with a rotating system. So we're going to do torque is moment of inertia times angular speed. That's the first equation we have. And then the second equation we have is that the rotor angle, if we're at synchronous speed, then it's not changing. But if it increases, then the rotor angle is going to be moving as well. So this is the derivative of the rotor angle is the speed. Other than that, we have a whole bunch of electric circuits here. We have 7 of them. We've got the A, the B, and the C, so 3 circuits on the armature winding. And then we have 4 circuits on the rotor, 2D and 2Q axis. So ultimately we have 9 sets of equations that we have here. And in the end, we're going to get Gen Rao at the other end of this in about 40 minutes. All right, so the stator winding is, we're not including any capacitance here. This is just a piece of wire wound around some iron. So it's basically an inductor. So if you go way back to circuits, all you have with an inductor and a resistance is you have a voltage is equal to current times resistance. Everybody knows that. Plus, think back, we have flux. Voltage is the derivative of flux with respect to time. So that's what this equation here is. So it's got a resistor and an inductor. And we have one of those on the A and the B and the C circuit. And then similarly, we have one on the 4 rotor circuits as well. And then finally, we have the derivative of the shaft is we have to do 2 divided by the number of poles, because if we have lots of extra poles, then it actually spins slower. But the speed then scales. So you have to scale it with the 2 divided by the number of poles. And then finally, we have the main mechanical equation, which is saying that the derivative of how fast it is spinning is the mechanical power minus the electrical power. And then textbooks usually throw in a term called friction and windage. Very shortly, we're going to throw that away because we just assume they build them so there isn't any. I think there's very little. I don't actually know. Does anybody have
I think you're correct.
I mean, they're built so precisely that the amount of loss, mechanical loss, is just de minimis. We just ignore it. I've never seen a model that includes that in a piece of software.
Sorry. So T in your equation is power, not torque?
The T here is torque. These are torque equations. All right. At this point, if you go look at a textbook, they're going to apply all of that stuff, and they're going to start defining an inductance, like between the A phase and each rotor phase. And the problem that you're going to have when you look at these books is if you think about what is the inductance between the A phase and one of these windings on here, well, this winding is spinning. So that inductance is going to be a function of where the rotor physically is at. And so when you draw out all the equations, I remember doing this in Pete's class, they're terrible. They're just, they get really complicated. They look like stuff like this. If I want the flux on A, it's this. I've got, here's an inductance, the self-inductance on the A phase, the self-inductance to the second, I can't even remember what the notation, I just copied these out of textbooks. But the point is, you then have a positional term that says as it's spinning, it varies with the position of the rotor, and they're very, very complicated. And what's going to happen here is we're going to thank all the engineers in the 1910s and 20s who literally took them decades to figure this out. We're like, you know what, if we just create this transformation matrix, kind of like Tom's positive, negative, zero sequence that I think most undergrads at least talk about that at the end of a class. You're like, hey, we can do this. It's like the last 2 weeks of your senior level course. You talk about fault analysis. This is similar idea. Tom talked about the number 1 paper was the positive, negative, zero sequence. Number 2 was this paper on the Parks. People call it the Parks transformation, but I think if you go back, Park kind of introduced the idea, but we don't actually use his transformation. It's a little different than his. But he had the idea of creating a matrix that takes all these ABC quantities, runs them through a matrix, and comes up with DQ0 quantities. And I'm going to skip all that. I think I watched Pete write on the board for about 1 or 2 lectures and showed that if you take all this mess, run it through some equations I'm going to show in a second, it turns into this. And you're like, okay, that looks easier. But we don't have ABC values anymore. We have D, Q, and 0 values. So the D axis and the Q axis are related to what I was just talking about. So we're going to skip all that. Basically, I tell you to, when you go home tonight, just say thanks to those engineers 80 years ago who figured this out. But then also remember, it took them decades to do so. It's not like they just sat down and were like, okay, here's how to do it. It's like, no, they thought about it. And then they retired and somebody else picked it up and they thought about it. And then, you know, it took a generation of engineers to figure this out. All right, so I'm going to introduce this equation in a second. This is a matrix, but we're going to turn our ABC values into DQ0 values by multiplying by a transformation matrix. And we're going to do the same thing if you wanted to go in the opposite direction. You'd take the inverse of that matrix. And we're going to apply this exact same matrix for voltage, for current, and for flux. We're basically taking the things that mean something physically and, you know, really turning it into math at this point.
So can I ask, because I forgot, what's the delta of the equal sign?
That means a definition.
Oh, okay.
This, we are defining it. It's not that these are equal because we figured it out. We're defining it.
Oh.
The definition is this is equal to this because we said so.
Okay. Yeah.
Yeah. So the transformation matrix is this. And this is and again, if you go back, look at the papers from the 1910s and 20s, people were debating. You can use different transformations, and they all kind of work. This one just happens to work out the best. And you can imagine, it's like, how'd they come up with 2/3 here and half and half? Why didn't we just do 1, 1, 1? And it seems more complicated than it needs to be. And the answer is they argued about this, I'm sure. There were probably industry meetings where people argued about what to do. So you can thank that at least we're arguing about less complicated things now. But this is the transformation matrix. It's, you know, it's not the same as positive, negative, zero sequence, but if you look at it, it's somewhat inspired by it. You still see that 2 pi over 3 that was similar to what positive, negative, zero sequence is. And the inverse of it happens to be this. And if you look at it, this transformation matrix, though, is much more complicated than the positive, negative, zero, because it itself is spinning. As the rotor spins, these equations are changing. So in some respects, when you first see this, you're like, isn't this just making it more complicated? But in the end, it does not. So if you take the equations we started with earlier, you take these equations, you take this ABC value, put it in a matrix, to multiply it by that 3 by 3 matrix, do some algebra for about an hour, you will figure out that the equations become this. They look very similar. I've got these rotor windings, these are all the same. All I'm messing with is the stator windings here. The ABC values are becoming DQ0. So they look kind of the same, but there's some extra terms that show up. I'm not going to go through that algebra. I mean, I did it when I was in grad school. I just believe it now. But
I think I'm good.
yes, exactly. Go ahead, John.
The delta shaft term, that's measured with respect to what reference?
That goes back to that's that definition of being here. It's not exactly this. It's like it's related to the angle between the. That's the wrong picture. That's out of Kundar. So it's not between the. No, it is right. It's between the Q and the A axis.
Okay, so that's the big thing.
Yeah, I mean, I'm drawing it here on a 2-pole machine, so it's a little more complicated if you add poles. But it's related to the physical angle of the rotor at that time. All right, so those are our equations. Kind of waved our hands. The equations are, we have the electrical system has equations that look like this. The mechanical system, I'm messing with them and skipping some more things, but adding in the fact that they're functions of the pole as well here. All right, so the electric torque derivation. Again, I'm going to skip a lot of things here that's are in a textbook. Friction and windage, we're kind of going to start ignoring that from here. The mechanical torque, that's coming from in the software, it's coming from the governor model. But you know, it's the steam. It's the amount of mechanical torque being created by whatever is pushing on the rotor. The electrical torque needs to be derived. All right, and if you go read papers, it's actually rather complicated. It ends up being that you create. If you look at all the variables over here, we got the electrical system. There's a certain amount of electrical loss, maybe from the resistance. There's the mechanical or the electrical system going out into the system. So then there's a certain amount of power that's being run through a magnetic field that's turning the electrical power into mechanical power, or vice versa. Over here we have the torque coming from the mechanical system. This is the friction and windage loss. We're ignoring that. This is the sort of amount that's being turned into the electrical system. Sorry, no, this is the amount that's going out to the mechanical system. Anyway, the point is, in the middle here, this is an electromagnetic field. All of the theory on this machine starts with the assumption that we don't lose any power in the transformation inside these electrical fields. And there's a huge amount of calculus that I mean, when I started making these slides, it took me like about a week to understand what it was saying, which made me go, I'm not going to talk about that in the presentation. But the point is, you start with this fundamental assumption, and it makes sense. It's not like the air is heating up. There's not loss in that electric field. And again, skipping the derivation, using that, it's called the conservative coupling field. Using that assumption, you can calculate that the torque has to be this, if that is assumed. And in the end, it's like, okay, it kind of makes sense. Power is voltage times current. We know that. Flux is ends up being voltage divided by speed because it's the derivative of anyway, if you think through voltage is the derivative of flux with respect to time. So if these are AC waveforms, the speed ends up being related in here. So it ends up making a lot of sense that it is equal to flux times current, like this. And then the pole value is in here. And this 3/2 value is just kind of showing up. It's part of the reason in the transformation matrix you use 2/3 because it ends up canceling out later. So, all right. And then we're also going to define a new variable called delta. It's the synchronous reference frame. This is what we're doing. This is what this is called. So we're going to assume that there is an angle that is equal to the synchronous speed. So this is 2 pi 60 right here. And then as the shaft physically moves, the rotor angle, what we actually call the rotor angle, is equal to this. Now in reality, the shaft is spinning. It's not like it's going anywhere. It's just sitting there spinning around. And we're going to make this definition. So again, you see the delta again. This is just defined as this. All right, so if you take these equations and substitute them back into the mechanical equations we have, we're now here. So if I jump back here, I'm taking these equations and then messing with them a little bit by putting in the electrical torque, and then delta changed here. Previously we were looking at previously we had this equation right here, that the derivative of shaft with respect to time is this. And now we have this one down here instead. And then we're going to add some different per unit values. All of these values here are actually not in per unit yet. And I'm going to skip about 2 or 3 pages in the textbook here where they talk about how do I per unitize things. And when you convert everything to per unit, you end up getting this. So now all these values that we have here are in per unit. So when I talk about P mechanical and I say 1, that means whatever the MVA base of the machine is. If I say 0.5, I shouldn't say MVA, the megawatt base of the governor model is right here. And a comment about omega. All right. All of our software tools, meaning ours, PS, all the different software vendors, are usually, but not always, consistent about saying, when we say omega, we mean the deviation from synchronous speed. So if you pull up a block diagram of a governor in simulator, and you see omega somewhere, most of the time that's going to be 0 at steady state because you're at 60 hertz. And so if we want something that's per unitized to be actual speed, we'll try to draw 1 plus omega. And that is true except for when it's not and somebody just made a block diagram and forgot to do it. So you're looking at a block diagram and you see speed. If you look at it, usually you can go, well, that will never be 0. So if it just says omega, and maybe you got a number divided by omega, clearly the block diagram's wrong. It's 1 plus omega. So usually omega means deviation from synchronous speed. We no longer, previously we had a value that was J in these equations. That was the moment of inertia. That's now been per unitized in things I'm not really presenting, and we end up having an H. Usually does anybody know why we didn't just say, why do we always have 2H? Why didn't we just say this is H tilde or something? I have no idea. Tom, do you have any idea? Okay, anyway, it's always 2H because that's what somebody decided. Could be the poles, maybe? I don't know. I have no idea. Anyway, it's always 2H. The electrical power or torque is over here. A comment about we have P, we have to divide by speed here because this is a torque value. So power divided by speed is a mechanical torque. And then a comment about this D term. All the software tools use this equation right here as their mechanical equation. And if you go look at a Gen Rao, a Gen Sal, all of our machine models include a damping term. It's really historical. Back in 1955, people did not go through and model this rotor that I'm going through right now, modeling all the damper windings. They didn't do it because they didn't have computers. They could have been literally doing this by hand. So they didn't include the damper windings, so they would often introduce like an extra term that was just, well, there's about this much damping, so that if the speed goes up, then it's minus here, so then the speed would try to come back. So what it means for you as a software user is if you get a synchronous machine model from someone who's done a test in the last 40 years, the D value should be 0. Because you're including the damper windings we're going through and talking about it. So you don't need this extra term because the damping is built right into the equations. So if you see a D value, it might, I don't want to say it does mean, but it might mean that an engineer was just tweaking a parameter so that the plots matched nice, but they really shouldn't have been doing that. That should be 0. All right, if you go look at Pete Sauer's book and the equations that we present, I mean, Power World, PSSE, PSLF, everybody kind of uses similar notation. You won't find a textbook that's exactly the same. Pete and Pi's book is as close as it gets. However, there's an extra minus sign. They don't use the exact same notation as us. There's one difference there if you happen to go look at their book someday. So what are all the per unit values? I didn't really talk about how we got to these, but the model that you end up using in software like ours, you're going to have omega s. Whenever you see that, that's usually 2 pi 60, or it could just mean that it's 1 if it's per unitized. In the equations I'm going to do in these slides, I will try to put a delta omega when I mean speed deviation, just to make that clear. We're going to have a stator currents. We're not going to talk about the ABC phase currents because then we'd have all those cosine of a position terms in there. So we're going to be in the DQ0 world. And we're going to have these are the terminal voltage. We have flux on the stator. And these are flux values on the rotor, really. And then we have a field voltage and a mechanical power. And then we have all these input parameters that the user adds to the equations. So I just skipped several pages in the textbook. So go through per unitizing everything. And the equations that we had before.
Tonight? You want us to do it tonight?
No. I don't even want to do it again. It's like if you go to grad school, you do it once and then never do it again. Because it's pages and pages of algebra. But basically, it's taking these equations. So we got 3 stator, 4 rotor, 2 mechanical. I just skipped a whole bunch of math, but we're still going to have 2 mechanical, 3 stator, and 4 rotor. So this is just the exact same equations, but with different per unitized values. And you do a whole bunch of math and you get to here. And we're getting very close now to what is used in the software tools. The only the difference is down here, the equations up here. These are, there's 4 different fluxes on the on the rotor, and we're assuming that the fluxes are that all the flux on the rotor eventually comes over to the stator and comes back. It's not like leaking out and disappearing somewhere, because again, the conservative coupling field assumes there's no loss in this transformation. So these fluxes up here are just the flux on the stator. So it's the relationship between the stator flux and the rotor fluxes. The other thing you might notice here is the 0 values all went away. I said this was the DQ0 transformation. I don't see any zeros. That's because I just skipped those. We're assuming we have a balanced 3-phase synchronous machine. So if it's balanced, then all the 0 values are 0. So in all of the software tools like ours, we don't include those terms, so they're not up here. All right, next thing. All right, I know I'm waving my, I'm trying to put like literally in a half a semester of a grad course into like 1.5 hours. Right? Is that about?
We talk about this in grad class, but it's usually an hour and a half, 2-3 hours.
Okay, I remember doing homework. I remember
might have talked about
a machine class, you would go through this in detail. All right. Another equation that we're going to mess with is right here. These are the stator fluxes. And how, actually, I'm including the zeros up here still. Haven't completely got rid of them. All right, these differential equations on the stator. One of the things that shows up is the derivatives here get multiplied by 1 over the synchronous speed. All right, what is synchronous speed? Synchronous speed in our world is 1 over 2 pi 60. So that is the time constant on this differential equation is about 2 milliseconds. So one of the approximations that we're going to make, as does everyone, is we're going to assume that these stator equations are really, really fast. I think these are taken out of, I'm pretty sure this is out of the, oh, there it is. It is out of Kundar's book. So if you were to look at the actual speed deviation versus time, what you're going to see in a software tool like Simulator is this dashed line. If we're to include these stator dynamics, there'd be some really fast dynamics that die away very quickly here. And things are going to be off a little bit. So this goes again back to Tom's comment. So by making this assumption, we just made the model wrong. And then it's like, well, how wrong? All right, if you go read a textbook, they're going to talk about things like integral manifolds and all kinds of stuff that's really confusing. And I'm always like, I know this isn't theoretically right, but basically we're saying, you know what, this term's really small enough that you basically just say, well, why don't we just approximate that it's approximately 0 all the time. And all of the math they talk about in a paper or a textbook really comes down to making this assumption. They just prove it that it's okay to do this. But this is the assumption we make about the stator dynamics. Basically, we make them go away by assuming that they're infinitely fast. And so instead of having these two differential equations, this term just goes away. And then we're going to have this equation, which just means that the terminal voltage is equal to the negative of this. So we just created these two equations instead. And these are the network interface equations that are going to show up in our transient stability models. If you multiply these out, so now I have flux on these are the stator fluxes, but remember there was also a bunch of algebra here that said the relationship between the stator and the rotor fluxes is this. So then you take these and substitute them down here, you group terms together, and then we get these equations down here. And eventually I'm going to get to the end here, and I'll pull up the round rotor block diagram and say, okay, this is where all this stuff came from. So trust me. So then we're going to define, all right, we've got a voltage is equal to resistance times a current. Okay, I got it, that makes sense. I've got with a speed times an XQ, IQ, all right, that looks like a complex number math there. I can see that that's maybe something I've seen before. And we come over here, and this looks kind of complicated. So what we're going to do with this term is say, well, why don't we define that as some internal voltage. ED double prime is equal to this, and EQ double prime, I should have put a delta here. We're just defining these. And then our equation becomes this. And this right here is close to what everybody does in software tools. So now we have these two terms here, where we're multiplying by essentially the per unit speed.
Is the E a constant, or is it dependent on?
No, it's these four values here are the fluxes inside the rotor, and they're constant. They're changing.
Okay.
This definition is defining how are these four fluxes created to create some kind of a flux out on the stator, essentially.
Okay.
So they're changing.
All right.
All right. Right here. Okay, so we have these two speed terms. All right. This purple speed term right here that comes out in the derivation, in most software tools we ignore this. All right. I've never really seen a paper that says this is why we ignore it, but I think I know why they ignored it back in the 70s when they figured this out. This is the this is going to show up as the internal impedance of our model. We're going to have a voltage source behind an impedance. That's where we're going with this. And so what it's saying is that that reactance is a function of the frequency. Well, you know what? So is the transmission line reactance, right? The equations Tom had up where you have transmission lines. If the frequency in the system is varying, then the reactance of a transmission line would vary. Most people never model that in a transient stability simulation because you're assuming it's not varying that much. And so we're going to make the assumption that, well, you know what, the internal impedance of a synchronous machine would also vary with frequency. But we're going to ignore that and just turn it into this and essentially treat this term as always 1. So the actual equations that get used in software tools is down here. So there's a, let me get to a picture. I should have put that up sooner. Let me just go open it in our help. Do a Google search on Gen ROU. The second link is Power Worlds. So we're eventually getting to this Gen ROU equations. What I'm showing right here is really, it's this. It's, you know what, I think I have it better on. It's this. We're getting to the point where we're going to model a synchronous machine as a voltage behind a reactance. That's where we're trying to get here, and we're almost there. All right, so now we have these 6 differential equations. So we used to have 9 differential equations because we had 3 stator, 4 rotor, and 2 mechanical. And we just took 3 of the stator equations and turned them into algebraic. So we still have 4 rotor equations and 2 mechanical equations. And then these relationships up here are just algebra. All right, we then have to talk about the field voltage. All right, the field voltage is down here. This is the field voltage actually coming from the exciter. Another term we need is something called the field current, and we're going to define that as this term right here. It's like everything else in here. All right, so at steady state, there is a relationship between the field voltage and the field current that's defined by a mutual inductance. It's an X value, so it's the mutual inductance times omega L. So typically, we will define this whole term right here as the field voltage. It's really the field voltage scaled by the mutual inductance, but usually we just call it the field voltage, per unitize it that way. Not the field, we call it the field current. And that field current, this term right here, is going to go back into the exciter models that Tom will present later. There's a field voltage coming out of an exciter and a field current going back to it. If you look at block diagrams that we have on our picture, you'll see the field current or voltage coming in here. This field current is going out. And so if you were to sum up everything coming into this summation junction, it's this. It's this big equation right here. So that's why we get to the block diagram. It's a little easier to talk about it here shortly. All right, I hate to tell you, but all we've talked about right now is one machine by itself against an ABC voltage out there. So it keeps getting more complicated next. But then there's lots of beautiful math that simplifies it. So next is, all right, we need to synchronize all of these machines, thousands of them across the system, all to one common reference. And this creates a whole bunch more math. So we're going to do a conversion that converts from the ABC values into I'm using capital letters here to represent something different than the rotor values. Or we're going to take this equation and multiply it by the ABC values to turn them into these capital letter values. And if you do that, and you make the assumption that the ABC voltages are balanced. So we're going to start with that assumption. So they all have exactly the same magnitude, and they're shifted by 120 degrees from each other. And if I multiply it by this matrix, and I do a bunch of math, and I hate textbooks because they always say, and you do some math and it's not that hard, and you get this. It's like, no, I'm putting the derivation steps and then letting you read them later. If you do all that math, it ends up being this.
It's intuitively obvious.
Exactly. Do a bunch of trig, and we've now turned our ABC balanced things into a magnitude and an angle.
Huh.
And also, if you notice, the speed's gone. There's no frequency here anymore, and all the frequency terms canceled out. And if you think about it, if I have two terms that are like this, where I have one value that's magnitude times the cosine of an angle, and I have a second value that's the same magnitude times the sine of the angle, complex numbers, we can say that's a complex number. So another way to think of it is, is right here. We can treat that as a complex number. But essentially, I mean, everything I just talked about here, this is exactly what a power flow does. We don't talk about sines and cosines in the power flow realm. We talk about magnitude and angle. You were making this assumption. It's the same one. Okay, so that's great. That takes us from, I have this. This is what we talked about earlier. This was the DQ0 transformation on the rotor. Then I have a transformation here that takes the ABC values and turns them into a DQ0 across the whole system. It's standard across everywhere. I can then take, let me jump ahead here to explain why we care. So what we're doing here is we're trying to get to the point where we have things on the rotor, the equations that I talked about the previous half hour. And then we have equations out here on the network. And we're trying to build a mathematical relationship of how we get back and forth between them. And in order to do that, we have to go through this ABC reference frame along the way. And most of the time, you will see people who've studied all this kind of skip all these steps. But there was something that came from it before. So in order to get from my rotor reference frame to what's called this network reference frame, I have to take the two giant matrices I had and multiply them together. So this was from before. This was the DQ0, where we took the ABC on the rotor and turned them into DQ0. And then this is the inverse of that. And then we then have to multiply this times that thing that took us to the synchronous reference frame, and we have to multiply these two matrices together. And again, you do a whole bunch of math, and at the very end, you get this. And this says that if I'm on the network and I want to convert from my network reference frame over to the rotor reference frame, I just multiply by this matrix. And then we're going to ignore the zero terms and kind of get rid of that in just a moment. So the beauty is all the math that I just waved my hands at kind of skips. Because we're going to ignore from now to eternity. Many textbooks will skip all of this and just say, to get from the synchronous reference frame to the rotor reference frame, you multiply by this. And I was like, well, where did that come from? It comes from a whole bunch of math that's going on behind the scenes. If you happen to want to hook a tool like Simulator up to an EMTP tool, the EMTP is working in the ABC reference frame, so you would have to go back and do these kinds of conversions every time step to be updating what the ABC values are. But most of our customers are never going to do that. So our final result of how do we get from the network reference frame into the machine is we multiply by these matrices that represent a rotation. And if you look at them for a little while, it eventually you realize that you can do, this is complex number math. You're just taking a machine value and multiplying it by, just rotating it by an angle. And the thing to realize is the rotor angle is right here. So as the system's spinning, or getting in or out of synchronism, that this relationship is actually changing. I don't really expect a lot of questions here, but go ahead.
In the earlier slides, maybe the alpha was just an angle.
It's just let me get back to it.
It shows up as an
It's right here. It's like at some random bus out there, there is a balanced voltage, ABC voltage, that's at it's at a frequency, and it's at some angle. Could be any angle. So it's literally it's equivalent to the angle of a power flow bus. It's like every bus has a different angle. Yeah. Mm-hmm. Yeah, but the beauty of going through all this math is that doesn't show up here. It's, whatever your DQ0 stuff is, the bus angle doesn't matter. All right, so now I have these equations. Well, we got those before. So then we have the network interface. All right, so these are the equations we have that describe how to take, I go back to my round rotor model here. The fluxes that I'm talking about are the states on these block diagrams. So they literally represent the flux inside the rotor. And they're dynamic. And if you take some algebraic combination of those, because this state and this state just get multiplied by a constant, come out here, and they're kind of being represented as a voltage then inside the machine. So we're then going to treat yeah, so we have a voltage inside a machine. We have an impedance behind, or a voltage behind an impedance. All right, if we make some assumptions about this, we can make our life easier. So it's 1965. I'm John Undrell, writing the first software tool on this. Perfectly reasonable to go, you know what? These two values are usually equal to each other. Maybe, maybe not. But if they are equal to each other, it's going to make my math way easier. It's going to make it easier to code things. So Gen Rao, Gen Sal always make the assumption that XQ double prime and XD double prime are equal to each other. And the reason they do it is because the software is easier to write. I completely understand why they did it. And it's usually close. And if you also make the assumption that as the system becomes saturated, which we'll talk about next, that those two terms don't change that much, then you can rewrite these two equations as a complex number equation right here. And this equation right here is a voltage with a complex impedance and a complex current. So the network interface is literally exactly this. And I can change from a Thevenin equivalent over to a Norton equivalent, and lots of things get very easy by making these two assumptions. Okay, I'm going to wave my hands a little later at things, but the more modern models like Gen TPF, Gen TPJ, Gen QEC do not make these assumptions, and they make the equations a lot harder, and I'm not even going to talk about that in this presentation. But it's hard in that it took someone like Tom or me or John Undrell a couple months to figure it out, but we only have to figure it out once. And others have figured it out too. So it's not like it's not that hard. All right, so here's our equations.
Jamie?
Yeah, go ahead.
Typical parameters for the XD and XQ double prime, how different are they when you put it in the more complex model?
Do you have any idea, Dimitri? They tend to be a little different. I mean, they're not going to be more, I think literally in our code, in Power World, we hard code it so they cannot be more than a certain fraction different than each other.
Oh, okay.
I think it's somewhere between like a half and 2 times. I'd have to go look at code.
Plus minus 50%.
Yeah, because as they diverge from one another, the approximations we make in order to handle that start causing numerical trouble. But they can be a little bit different. Okay. An aside, later tomorrow I'm going to talk about renewable models. All right, one of the really nice things about the synchronous machine model is we're modeling it as a voltage behind an impedance. So if I come in there and fault that, make this voltage go to 0, there's actually not a problem numerically. I got a voltage, I got an impedance, okay, I just get current. It's, you know, moving around in there, no big deal. It doesn't numerically fall apart. All right, the renewable models we're going to model as a constant current injection, and that causes all kinds of trouble when you fault it, because suddenly you're trying to push current into 0 voltage, and what does that even mean? It's like, you know, what is the, for instance, what is, if the voltage here is 0, the magnitude is 0, what is the voltage angle? Who the hell knows? It's the different, you know, it's the angle between the two vectors, but it's gone. So there are all kinds of numerical trouble that's going to happen with those, and I'll talk about those tomorrow. And I kind of already mentioned this. If we allow this, then things get more complicated. All right, so next we have to go to saturation. And this is where things get very complicated, but then there's a lot of hand waving. So these are the equations that we kind of waved our hands at modeling. I've now turned them in from those equations into a block diagram. It's a little easier to kind of look at with pictures then. So when you're right here, the derivative of this state is whatever's going into the integrator. Tom's going to talk about block diagrams in a little bit. So I'll let him mention that. But just something to tell you, for someone like me, I went to grad school in the 1990s. If you were in grad school in the 1990s, you worked on economics. That was what people worked on. So I worked on OPF, electricity trading. It's like I should have gone off and been an electricity trader. Although I wasn't the guy after me, but one of Tom's old students actually went to jail at one point. Didn't he?
He was fined. I don't think he went to.
He didn't go to jail. He took the topic that I started on of like how to basically intentionally create congestion so you can make more money, and he just went too far with it. But anyway, my point is, I went to grad school. I got a PhD in electrical engineering. I took stuff like this. Yeah, I took stuff like this. I came back to this 10 years, and Tom's like, we're going to work on transient stability now, and he put stuff up like this, and I was like, what the hell is that? What is S? What is that? So if you look at something like this and you go, what the hell is that? Then so did Tom and I when we first started looking at transient stability 10 years removed from having studied it. So don't feel bad if you're like wondering what this is. So did we. All right, so anyway, on this block diagram, this is all representing derivatives, states, and things. We haven't included a topic called saturation. Okay, yeah, I can already talk about that. Yeah, and this is, again, where I might pause for a moment. Thank everybody 80 years ago who figured all this stuff out. Okay, so we haven't included saturation yet. It's a whole bunch of synchronous machine models. The Gen-Rao, Gen-Sal models are kind of what I'm going over, really. And we'll talk a little bit about these other models here shortly. But the first thing we need to do is talk about saturation. I'm going to kind of wave my hands at a lot of this, but the idea is we usually talk about, on an inductor, that the voltage is the derivative of flux, which is the number of turns times, I'm even forgetting what some of these things are. And we make the assumption that the flux is equal to some constant times current. This constant is what we call inductance. All right, in reality though, if you look at how does the flux in, going through a magnetic material as you wrap wire around it, change as the current increases. If you're talking about an inductor, you've got a straight line. It's a linear relationship. Or what is my 6th grader says, directly proportional. I'm like, you mean linear? No, we call it directly proportional. They're not talking linear yet. Directly proportional, it goes up. In reality, as you push more and more current, more magnitude of an AC current through it, it saturates. Essentially, again, I don't really remember exactly why. It's like the flux like gets crowded, it bumps into it. Why does it saturate? I don't really remember. But there's something about the magnetic material that at some point you have to push more and more and more current in order to get flux out, and it will saturate. And different material will saturate in different ways. So this is a slide Tom had gotten off Wikipedia that looks at how does sheet metal steel, silicon steel, all these different kinds of materials. The kind we're talking about here is iron. So ours looks something like this curve on number 6. So actually what I'm presenting, if we were using a different kind of material, some of these curves would be hard to represent. So the initial part that's linear is what we are modeling up until this point. So we're going to talk about, well, what happens when it saturates.
Yeah, I don't think they're building a lot of iron.
Oh, you're right. So which one is it?
Silicon steel, magnet steel. Maybe.
I'm sure some of the high stuff up there.
Okay. Anyway.
The gist is it'll saturate.
It'll saturate at some point. Another thing that a magnetic material will do is as you go up, it's got this something called hysteresis, where it kind of, some of it gets stuck in there. All right. They are going to build these generators in a way with laminations, and actually that's more for eddy currents. That's something different. But anyway, all I'm going to do is wave my hands and say we're not going to model this. We're not going to model the fact that there's like return path that's like this. We're just going to model it as though there's one path. So models like ours do not include hysteresis. So what we're going to have is I'm going to start talking more about current and voltage. If you think about, we're talking about AC waveform. So if I have an AC waveform, right up here. Is this erased? Making sure I'm not using it. Yeah. So we have a voltage waveform at some magnitude times, let's just ignore the fact that there's angles and stuff. It's cosine omega t. But actually, let's call that flux. You remember we're talking about voltage, the derivative of, sorry, not voltage. Voltage is the derivative of flux with respect to time. And we're going to be talking about phasors and things at 60 hertz. So the derivative of this is just A omega. Derivative of cosine is minus sine. Is that right? So voltage is, if you could think of it as flux times omega e to the j pi over 2. I can't remember if it's plus or minus in there. But the point is, all you're doing is taking the flux. If you take cosine and sine, they're just 90 degrees out of phase with each other. And the magnitude increased by omega. So really when we talk about flux and voltage in a synchronous machine, they're similar to each other. They're scaled by speed and they're shifted by 90 degrees. But we're looking right here at magnitude. So the magnitude of the field current versus the magnitude of the AC. So this is a DC current and an AC waveform magnitude. So we're just going to talk about terminal voltage instead of flux, but they're related to each other. If you go do generator testings, I was just talking to Steve at EPA here. He's going off to do generator testing tomorrow. Are they going to do this test tomorrow? They got an open circuit generator. They're going to increase the field voltage, which increases field current, and they're going to look at what is the terminal voltage. They're going to trace this curve. And if there was no saturation, they'd get a straight line. But there's going to be saturation, and they're going to do a physical test out there that gets this blue line. All right?
It's almost the first test we do.
Yeah, because it's off.
Also define the field voltage base.
Okay. All right, so this is a test that will be done. All right, I like to take this curve that you traditionally see, because in software it's easier if you flip the axes. So I'm going to do voltage or current versus voltage instead. So this is the same curve, just flipped. The axes are flipped. So if you think about it, the way we're going to represent it in software is we got a straight line. Those are all of our X values that you put in a synchronous machine. They're the unsaturated inductance values. So when we start saturating them, we're going to have to add some extra term. But the values we're giving are related to these lines. All right. The actual amount of current needed to get this voltage is the blue line. So essentially the green stuff is the extra current we need. So if you think about it, the gray line is what we have. If we split that up into two pieces and say I've got a red dashed line and I have this purple line and I add them together, then I get what we actually have. And this purple line is the extra stuff that's coming from the fact that the magnetic material is saturated. So different software tools are going to do it differently. I like to joke about this. If this was today and people like Dimitri and I were in a room, somebody in the room would be like, we need to define that really accurately. We should put in a 10-point piecewise linear curve to define the saturation super accurately. That is what would happen today. Thankfully, in 1970, people didn't have as good at computers. So they said, you know what, why don't we just pick 2 points, choose those, and we're going to define a function. So the advantage is there's only 4 input values here. Or actually, there's only 2 on a synchronous machine, because we assume that the x values are 1 per unit and 1.2. And you just give us these 2 points. And then you have to pick a function that describes how the extra current needed as you increase voltage varies, and you just define the shape by a function. And one of the things that Tom found out when he did, that was a BPA funded project, I think, back in the early 2010s, when Tom was validating PowerWorld, PSSE, BPA's old tool, PSLF. One of the things he found out was the software tools don't use the same function. Right, Tom? We found out that PSLF uses this function and PTI uses this function. And as long as you're in between, it doesn't matter that much, but you will get different answers. So this function here is one we call scaled quadratic. It's a quadratic function, but then it's divided by the input also. So the function will look something like this green line right here. And as long as you're between these 2 points, all of these functions give similar answers. All right, this is just describing how to derive from input data what this function is. We want the curve that's increasing in here, not this other one that matches the input data. This is what we call the quadratic function. Again, the values look similar in between. And if we compare this curve to this curve, the green part in between the points is about the same. And then some people like to use an exponential function instead. But all that these things are doing is they're trying to describe this purple curve with only 2 points. And just to comment, one of the assumptions is that as the voltage goes up, the saturation goes up. But that doesn't mean that the user can't put in input data that flips those, which makes no sense. So software tools have to deal with that. But
so Jamie, it's just hard-coded for all time that the voltage values are 1 and 1.2?
On the synchronous machine models, that's what it is. Yeah. On the exciter models, there's 4 input parameters. But actually, let's just go look. So if you look at the Gen ROU model, down here there's 2 input parameters for what is the saturation at 1.0 per unit field voltage and what is it at 1.2. But if I go look at, say, an exciter, actually this one already has one, you'll see 4. There's E1, saturation 1, E2, saturation 2. But they're similar concepts and they're giving it 2 points. Yeah, I mean, it didn't have to be that way. That's just what software vendors decided. All right, so if you have this test that says in order to get this field voltage, I need this amount of current, then it's very natural to take the Gen ROU model that we derived earlier and just add in some extra current or extra current, extra field voltage, whatever. And that is what happened in 1960s. They had a test. It made perfect sense. Just take the flux and the stator, run it through here, and add in some extra field voltage that is needed to get this AC voltage at the output. So this, what was chosen for this model came right from the empirical test. So remember, this is the field current right here. So we have flux, which is related to the voltage magnitude at the terminal. It's a bit of hand waving here, but the test that is done is an open circuit test, which means that the stator current is 0. If you go through a lot of math, you figure out that during open circuit, the Q axis is actually all de-energized. So this whole thing down here is like not there when you're doing the open circuit test. So really all you're doing is up at the top, you're just saying I've got a voltage at the terminal and I'm going to run it to get a magnitude, but I already have a magnitude because this one down here is 0. And then I'm just going to add in some extra value from the saturation function. So, I mean, it was done that way because that is the test that is used to create the model. All right. Down here, I just said that when you do the open circuit saturation test, this entire stuff is de-energized. So that value right here where you're saying, oh, and there's also some saturation down here on the Q axis, we're not testing for that at all. The assumption that is made is, well, there's a certain amount of scaling from saturation on the D axis. It's probably the same on the Q axis. Probably. The whole iron's getting saturated. It would make sense that the angle that the flux is going probably doesn't matter that much. So that ratio right here, it's not clear when you guys are looking at it because it's like it's XQ plus XL, but these two values happen to equal the mutual inductance. So that's the inductance that's inside the iron. So that scaling term is just coming from that. There's no test behind that. It's just that it's an assumption. All right, other things related to this. The saturation is not a function of the current at all on this. So as the armature current, as you load up the machine, it's only a function of the voltage at the terminal, which testing that Dimitri and folks at BC Hydro, they know that's not true. When they look at saturation, it changes with loading. I don't think anybody has a great handle on why. I have some guesses, but anyway. As an aside, it's funny, Pete, I love his book, but what I think happened is he worked on this like the first half of his career, and you can see kind of at the end of the book he had a lot of pieces that he kind of just abandoned. I think he just got sick of this topic. Because when I would ask him about it, the only thing he would always tell me is that the Gen Rao and Gen Sal models are wrong. That's what he would always tell me that. And up until about 2 years ago, I didn't know what he was talking about. And what he's talking about is what was done right here to take this test and just insert some extra current right here actually violates a whole bunch of assumptions made during the derivation. Because it's essentially saying that only this particular flux is saturating. But really, all 4 of these represent fluxes on the rotor, and there's a relationship between them, so they should all, saturate together. And he had a paper he wrote in the early 90s that described this and said Gen Rao is wrong, but I think that's like the last time he thought about transient stability because he kind of moved on from that.
Did you tell him that all models are wrong?
Well, correct. But the fact is, actually, if you look at his paper, what he didn't get to here, but what he was saying was, instead of adding it in over here, which is right where the test is at, instead, if you just sort of add in some extra current, then it still satisfies all of his theory. And this model would have been just as easy to implement, but no one ever did. All right. This, I'm just going to kind of skip a lot of these slides, but they're useful. If you want to initialize this model and you were writing your own software, but you buy ours so you don't have to. This is walking through how do I take a saturated model and actually initialize it. And in the end, you get a rotor angle that's down here. This is the Gen Rao thing, but I'm just going to skip through this. If you ignore saturation, it's actually much easier, as most things are. If you ignore saturation, all those equations end up being, you can just calculate it with a circuit equation. This is not the same circuit equation we use on the Gen Rao model. If you look back, the impedance here is R plus XQ double prime, but to get the steady state value, you have to use XQ itself. But it just so happens if you run this, then the angle you get right here is the rotor angle. But when you have saturation, it gets more complicated. And then you have to initialize all of the rest of it. So what's going on here on the block diagram, if you want to initialize this value, you have the flux on the D and Q right here. It's actually, you don't have that initially because you have the ABC values. In order to get the DQ values, you have to run it through that matrix that include the rotor angle. So you don't know the rotor angle. That's part of initializing. So it is kind of complicated to initialize this because the rotor angle has to be calculated as part of the initialization. But anyway, I'm just going to skip through that part. All right, a comment on the Gen TPF and Gen TPJ models. All right, the advantage of this model was it included the ability to allow saturation to vary with stator current. This model, it came from testing that Dimitri and John Underl and others did, and I think they just kind of added a term because it matched the test data. So that was an advantage. There was another advantage of the model was you could have the 2 double prime impedances not be equal to each other. And the big advantage was it matched tests that were done better. So it was matching things better. The biggest thing it was matching better was the field voltage and current. So this is the Gen TPF and J model. So a lot of the models in WEC are like this. One of the things with the model is, if you look at the block diagram for this model, the leakage reactance is not in there. So I think somewhat unintentionally, they made an approximation in the differential equations that later on we were finding maybe we didn't need to make. But the big change is right down here, that the saturation function itself is no longer just a function of the voltage, but it's also a function of the terminal current, the stator current. So as the machine is loaded, the saturation changes. All right, so several years ago, Quincy Wong, he was at PowerTech, then he went to BC Hydro, was noticing some troubles with the Gen TPF and J. And mostly because, again, the field voltages and currents didn't match. All of these changes with related to saturation that we've been kind of thinking through in the last 5 years, there'll be another 5 or 10 years before people switch to this model. But all of them, they make the system a little more accurate in mapping how the field voltage and current changes. All right. So one of the questions that would be natural would be, why does anyone care? Why does it even matter? And I think historically it hasn't mattered that much. I think the reason it's starting to matter is because people keep telling folks like you, we need to model over and under excitation limiters. All right, so in an old Gen ROU model, actually Tom doing GIC studies, the first GIC studies he did were included this stuff in transient stability. He was like applying a big solar flare coming and hitting Wisconsin, and he expected a voltage collapse. And he ran the studies, and everything was fine. And he was like, this is ridiculous. And then he went to look at the generator VAR outputs, and they were all like 5 and 10 times higher than the steady state limits. And it's because in your models in transient, you don't model over excitation limiters. So if you look at the VAR output of a generator during a transient, during the fault, it goes really high. And you're not modeling the fact that something's going to clip it because the field voltage will go too high. So the first thing Tom had to do that study was to go input some sort of crude over-excitation limiters to prevent that from happening. But if you're going to start modeling these, suddenly your results matter whether you get the field voltage and current correct. So if you start adding those, it's going to matter more. So, I don't know. You could listen to this and go, okay, that's a good reason not to model those. Because then I can keep using the synchronous machine models I have. But, as you start modeling these things, then it matters more. So the Gen QEC model is a new model in simulator. It builds off of the Gen TPF and J model. Essentially, I'm going to skip these slides, but right here, this is Gen ROU. Instead of adding in saturation as like an extra additional term here, it's going to assume that all the impedances in my model are scaled so that there's a leakage reactance. That's the part that's represented by the air gap. So that is not going to saturate. So if I have XD double prime, if I subtract off the leakage reactance, essentially that's the part that's inside the rotor. If I assume that that just scales with some multiplier, and I do that to all the constants, including the time constants, including the field and current and voltage, and I scale them by some multiplier for saturation, then I can do this instead. So instead of the addition term that I did with the Gen ROU and Gen Sal, because that was the test that I had, if I instead just scale by adding a multiplier, and literally this SAT value is the same everywhere in here. This is essentially what the Gen TPF and J model did, but I'm applying it to the Gen ROU model instead because it includes the leakage term, so these differential equations will match. Whereas with the Gen TPF and J, they did not.
So is the saturation term a function?
It's
I must have missed it.
No, I didn't. It was. I kind of skipped it. The saturation term is 1 plus the saturation function.
Ah, okay.
And oops. So that will work. We think that will work better. The thing that Quincy at PowerTech has found is that as he loads the open circuit test, you're down here as you vary voltage. When you come up here at 0 voltage, I mean, you can't really get to 0 voltage, right? But as you vary the field current when you're loaded, what he's finding is if the ID is negative, then you tend to be over here, and if you're positive, you tend to be over here. So the whole curve is shifting all the time. So what Quincy talked us into was just adding an extra term right here that kind of literally changes the slope of that curve as the thing is loaded. My coworker Sarah and I really didn't like this for a long time, and we tried to come up with something that was a little more beautiful theoretically, but we've given up. This matches his test data. One of the things we don't like about it is it kind of violates the idea that the D and the Q axis saturate the same together, because we have a term here, but we don't have a term right here to make it symmetrical. I never really understood why Quincy did that until I sat down to code it. And if you include a term here, it makes the code really, really hard. So I was like, Quincy, that's why. It's like some of these decisions get made because the software gets more complicated. And it's like, is it worth it for the accuracy you get? So he's got an extra term here that's similar to the KIS term that's in Gen TPF, or J, but it's a little bit different. So, all right, one last comment about the synchronous machines. If you want to switch from a model you have now over to, say, the Gen QEC model, it is not appropriate to just take the parameters you have and copy them over. Tom mentioned this kind of in passing in his earlier presentation, but all the input parameters go with the model. They're intimately tied. So just because the parameter names happen to be the same doesn't mean they mean exactly the same thing. They're tied to the model. So one of the, a problem that happened in WEC when people switched over to the Gen TPJ models, I think a lot of people just took their Gen ROU and Gen Sal model input parameters and copied them over, because that was way cheaper than paying somebody $100,000 to do a new test. It would have been better to leave the old model with the parameters that were fit to it and wait until the next time you do a study, and then you're fitting the parameters to that model. So you can't just switch.
If you save the test results, can you just retune it to the new model? Okay.
Absolutely. You could go back and retune it. Yeah. Someone like BPA would have the staff in-house to do that. Most of
course.
Huh?
Of course.
Yeah, most other utilities have to pay someone every time they want to do that. All right, so I guess my hope was we'd come up with something better than Quincy. After Sarov and I working on it off and on for a couple of years when we had time, we eventually gave up. We'll leave it to, nobody's revisited this model in like 30 years, so we'll wait. Somebody else can revisit it 30 years from now. All right, and the last one just kind of walks through. If you're inside simulator, you can, when you're in a simulation, you can actually go look at these DQ values if you want. You come in here, the terminal values, it actually lists the direct and quadrature internal voltages. Most of the time you're not going to look at that, but these all come from there. So here's the D, and this is the voltage and magnitude angle, so I can get VR and VI. I can then transform that over to the DQ values and get the values on the dialog. It's just showing you that these are truly related with all this math that most of the time you will never look at.
Jamie, did he say why it is named Gen QEC?
It is called QEC because it allows for quadratic or an exponential saturation. There's an input parameter. And Quincy and Sarov and I kind of settled on this being, it's like a compensation term. So the C is there's an extra term that's compensating for as the load, as the stator current changes, the saturation changes.
So it's Gen with extra compensation?
Yes, it's I don't know. I was trying to call it Gen TPW for Power World, but they didn't like that. That's why it's called that.
So has it been used?
I don't know
in
if
any
Quincy's
of the testing to show that it does a better fit. Of the
Quincy
data?
has done some testing to show that on his. I mean, granted, Quincy has a particular generator that had particular problems with the old models. I suspect most generators it wouldn't make a big difference. So, but I mean, no, well, it could be. It's quadratic exponential compensation. That's what he called it. I suspect if we Gen QEC, you'd have to go look. That's all. Yes, the cool thing about Power World's, here it is. Here's Quincy's. The cool thing about putting our help documentation on a public website is we're always the first link in a Google search. Yeah, so I think he's calling it. Yeah, he walks through kind of, I don't know. Quincy thinks about things more in these diagrams. I always get confused by these, but it's another way of thinking about the block diagram. Yeah, single, yeah, there it is. Quadratic or exponential, and then he calls it with compensation. Yeah, a simple field current compensation. So that's why it's called that. All right, I know that's really technical, but it's kind of gives you a flavor as to where these models come from. And mostly I always go back to the slide to thank people for figuring it out before us. I mean, it took me, I started working on this, Tom started in 2006, I probably started looking at it in about 2008. I don't think I understood any of this until about 2016. It's like I can code these equations without understanding where they come from. So, you know, there's a lot of history behind it that isn't really taught anywhere because it's, you know, people already figured it out. So, all right. So where are we supposed to eat lunch?